Thank you very much for the introduction, and also thank you very much for the invitation. I'm very honored to be here, and especially in this impressive environment here. It's fantastic. I was asked to talk about tendon mechanics on a macro scale, and I will do my best. But first I'll just show you where Norway is, if you don't know, and show you where my institution here, the Norwegian School of Sports Science, which is a sports university located right in the outskirts of Oslo. And in the summertime it normally looks like this. In the wintertime it's not raining either, just like here. And in the wintertime this picture could be taken maybe a few hundred meters from my office. So if you like cross-country skiing, that's a good place to go. Tendon mechanics on a macro scale, and it may in reality be that the next 20 minutes will go with a little more talk about not all tendons but more the large tendons, and not only tendons but also, because these structures are linked together, muscle tendon units. I was asked to talk about, or to take basis in this present paper here that was published just last year. It's a review paper in the Exercise and Sports Science Reviews, and it deals with heterogeneous loading of the Achilles tendon. So you can read more there if you are interested. So Michael showed you the bicycle and chain analogy. I will show you another one, but it's basically the same starting point here. This is what you can see in your anatomy book. This is how human movement works. You get some neural activation, you get some contraction, you get some force transfer through the tendon, and you get some joint movement. And this is the basic understanding. But if you look into the real world, or if you look into sports like we do in our department, and I hope I am able to play a video here. This is a presentation from our lab. This is a handball player who comes in and does a side cut movement and then makes a score. And as you can see, this is a lot more complicated than what you saw just before. There's 3 dimensions all of a sudden, and as you know, the world functions in 3 dimensions. Another example of this is simply an athlete here with force or pressure transducers below the feet, and you can see that in real life you get pressure distribution in different ways than you do in a lot more complicated pattern. If we move again back to the anatomical drawings here, you can first of all perhaps remember that we talk about plantar flexors. It's always the triceps surae muscles, but just remember that there are also other plantar flexors lying deep below the triceps surae here. But this is not my main point. The main point here is based on what you saw on the previous image, that if you are in a situation where you want some force on the outside of the foot, what is then the strategy or solution that you will ask your physiologist to do? That is to activate some muscles that are on this side of the movement axis, on inversion axis, or even perhaps a part of your Achilles tendon or triceps surae here. These muscles are in a good position to create pressure over here. It could be another situation where you want pressure on the inside of the foot when you do your side cut maneuver or whatever you do. And in this situation you need muscles activated that are on this side, on this outer side of the eversion axis here. And that could be peroneus muscles. They are very weak and not good plantar flexors, but you could also include some of the Achilles tendon here, if not all. So the whole talk here evolves around this. Is it possible to fine-tune muscle contraction to better enable these more complex movements that we see? And the questions that I will try to address, and unfortunately perhaps not answer completely at least, is then if this has to happen, what I just showed you before, then you would suspect that tendons can transmit force, not like the bicycle wheel or the first drawing I showed you, but in a non-homogeneous manner. And in line with this, since we're talking about muscle tendon units, you also have to discuss if muscles are mechanically independent and how this interplay goes on inside a close packed limb of a human or an animal, if you're interested in that. So this is the outline here, and the question start with this: if tendons transmit force homogeneously, you can look at inside the tendon, or you can look in a more longitudinal direction from the tendon to the aponeurosis. This here is an image that is from 1872, and it's not a human Achilles tendon. It is an Achilles tendon, or a triceps surae, I should maybe say, of a beaver. But it's interesting because it's in the Journal of Anatomy and Physiology that doesn't exist anymore. But this is a veterinarian at the time who looked at different species and looked at Achilles tendons and found this tendon rotation, and not only in beavers but also in other species, including humans, and reported this with a drawing. Later on, in the 14th, there's a paper that's always cited, and this is an Achilles tendon seen from proximal to distal, also showing that some of the tendon relates to the gastrocnemius and some of the tendon relates to the soleus. And this is anterior, posterior, medial, lateral, so I hope you follow. But as you move down distally through the tendon, you can see a certain rotation of this part of the tendon. So what starts being on the lateral side perhaps ends more on the anterior side, and what starts on the medial side perhaps ends more posteriorly. So there's a twist in the Achilles tendon. And if you simply take a picture of a cadaver, you can, it's maybe hard to see on the screen here, but if you look carefully, you can see this twist where the medial gastroc here twists behind, and the lateral gastroc kind of twists in front and goes to the other side of the calcaneus down here. These are quite beautiful pictures where Achilles, and I know Tony Arndt, who's also in the room, has some similar descriptions of how the Achilles tendon does this turn going from proximal to distal. These are came out of Cologne, of a colleague we have there. Also, some fairly recent studies indicating that the Achilles tendon, this is maybe difficult to grasp, but this is the calcaneus here, and this is a human Achilles tendon that's split into different compartments. And in a very recent study that came out last year, titled "The Twisted Structure of the Human Achilles Tendon," in fact, quite a few subjects were split into different groups based on the twist of the tendon. And some people tend to have a large twist, and others tend to have less twist. But anyway, it's quite clear from these studies, at least, that there seems to be a distinct connection between the fascicles of the tendon and muscles further proximal. The question is then if this has any functional meaning, and that we will come back to. But before we do that, just a quick look at the patellar tendon also. The patellar tendon, some people call a ligament, and that is also because it connects bone to bone. But if you look at the patellar tendon, it doesn't seem to have such a twist. It seems to have, at least in the sagittal plane here, it seems to have parallel fascicles. Although if you look in the frontal plane, the fascicles do converge, but it doesn't seem to have the twist there. And some people have previously put forward then that this twist versus non-twist has to do with the function of the tendon. And in rope design, you can also find twisted ropes, and these types of ropes are good for strain. They're good for absorbing and storing and releasing energy, where it may be a bad picture, but more parallel ropes here, they are good for position control. They have low strain. They don't store perhaps as much energy as these types of ropes. So this could be an argument, and it's not only my argument. It has been discussed that there's position control tendons and energy storage designs for tendons, and you could also say it's a long and thin versus short and thick anatomic design simply. So the question is then if the tendon is loaded non-uniformly, and there are data to suggest this. These are some older cadaver data showing that there can be different stresses in the tendon. I'll come back with some more data a little bit later. And it can be medial-lateral force differences also, depending on how the structures are loaded up. In our lab, and actually in Michael's lab some years ago, a study was done using the ultrasound here where we were interested in how the Achilles tendon underwent deformation during loading. And part of the study was to get a good fix point in the ultrasound pictures. A needle was inserted transversely through the Achilles tendon, and subjects were then asked to do high force plantar flexions. And long story short, when some of these needles came out again, they were not straight anymore. And this is at least some kind of evidence that perhaps not necessarily the Achilles tendon undergoes uniform loading. This was taken a little bit further in this study, where with ultrasound and then measured higher up, we were able to show that there's a difference depending on the knee joint position, and there's a difference in how the muscles are moving. So with a straight knee, with a flexed knee, the soleus here seem to be moving more, whereas with an extended knee, the gastrocnemius on the back side seem to be moving more, indicating perhaps non-uniform loading at the tendon level, but indicating. As you all probably know, there are new technologies with ultrasound, and we have not used these, but the speckle tracking here, there's emerging data coming out that depending on where you are in the tendon, you can also show different movements of different layers of the tendon. And I think this is a promising tool that also will be coming up and being even more improved. Yeah, I'll just jump this and skip to this one here. This is a cadaver preparation, not using ultrasound, but also a nice preparation, I think, where these authors in Cologne were able to put triceps surae specimens up here, and they had different beads inside the tendons, and they were able to look at the moment at the calcaneus, and depending on the activation or the loading of the muscles here, they were able to show differences in strain, also depending on the calcaneal position. So if you were in an inversion here, you would see greater strain on the lateral side of the tendon, whereas if you were in an eversion position here, you would see greater strains on the medial side of the tendon. And this is also to illustrate that perhaps something as simple as anatomical configuration or joint position simply governs loading of the tendon, and may be used also in the clinic to perhaps treat pain or disorders in different areas of the tendon. And finally, in this part of the talk here, talking about the patellar tendon, we have not so much data, but these are just data that came also out of Copenhagen, showing that at the patellar tendon there's also differences in the anterior side and in the posterior side of the tendon when it comes to peak stress and even the mechanical properties. So there may be within the same tendon that's made of the same tissue, at least supposedly, there may be differences in mechanical properties, and these may play a role for performance and function, and may also play a role for injury. So this was the intratendon part. The thing about the tendon aponeurosis is basically the same thing. We have two tissues that are made of the same tissue, but they are connected in series. And is there a difference in their mechanical properties, and does this have any relevance for function? And this study I mentioned before with the needle was actually, the idea was to put in the needle in the tendon and look at deformation here, and look at also deformation of the aponeurosis further up with the same load. And these authors were able to show, and it's almost impossible to see on the screen, but they were able to show differences in mechanical properties of these tissues. That means differences in stiffness from the aponeurosis to the tendon further down, even though they are made of the same tissue. And this is in vivo data, obviously collected with ultrasound. And this is in contrast to ex vivo data where the muscle fibers are not active. And the whole explanation, or at least the hypothesis for this difference, is that exactly the muscle fibers have an influence on the mechanical properties of these tissues. So if you have a flat sheet of aponeurosis with muscle fibers incorporated, this changes the connective tissue and the mechanical properties. So that may also be something to consider. And these data are backed up with now Taya is not here, but they have some data showing differences in the strain of these tissues, of the soleus, aponeurosis and tendon, depending on where you measure along the tendon. So it seems that there are differences, even though it's the same tissue, it seems that there are differences when you look at it functionally. So the last part of the talk here is if muscles are mechanically independent. Remember the hypothesis of the first slide here, talking about how is it possible to fine-tune the movements or the moments depending on what you want. And the first question is then if the muscles can be non-uniformly activated, and the theory would then be that here you have two muscles, so one is activated a little bit, the other is a lot. Are they connected to the same tendon? Will there then be a shear loading of the tendon in here? And there are, this is, I think I showed you maybe this slide before, but these are one of many, not many, but one of some studies showing that there can be non-uniform stress in the Achilles tendon based on the different muscle contributions there. So moving up to the thigh and the quadriceps, I lack a slide here, I'm sorry, it's a video, but it didn't come out, but it'll be okay. Moving up, this is a sine phase image, MRI image of the thigh, and it's hard to see what is what here, but basically this is looking at the quadriceps, and this study here that was about 10 years old showed that looking inside the quadriceps here, looking at the rectus femoris and the vastus intermedius, there are differences in how people use these muscles. Some people tend to use one of their knee extensors more than the others. Others tend to use the other one, and some have a balance between these two muscles, indicating in the quadriceps you can also choose to activate differently. In our group we have used another approach to an ultrasound. We have used a lot of ultrasound, but also we have used this PET, positron emission tomography, to visualize muscle activation. I'll just show you briefly some data. What you do is you eject a tracer, you have the subject perform a type of work, and you can then visualize which muscles took up glucose, which is at least an indication of which muscles were active. And you get pictures like this. This is the MR picture over here and the PET over here, and this is a complex movement. That's not my point. My point is this here. This is a subject who has been doing plantar flexions, and you're looking just above the malleolus here, and you see glucose uptake in the deep plantar flexor muscles. Moving further proximal, now you see still the deep plantar flexor muscles here. You see the aponeurosis sheet here, and here is the soleus, and this subject is not using his soleus for plantar flexion, which is totally unexpected. Again, further up, again, the soleus is here. This subject is basically relying on other muscles for plantar flexion. So my point here is that this is a little bit higher up, but it doesn't really matter. My point here is that there may be differences in how muscles are used and activated compared to what you normally think, and you have to take this into account. This is a study that came out a couple of years ago using the same technology, looking at healthy and Achilles tendon injured subjects, and again it was possible to see differences in how these subjects activated their muscles. So finally, it seems that there's non-uniform muscle activation, but finally, could it be that also force is transmitted between muscles that are located very closely in a limb like a human limb? And this discussion doesn't come out of nowhere. It was an editorial some years ago in the Journal of Applied Physiology questioning if muscles are mechanically independent or if they have an interaction, you might say, a mechanical interaction. And there's another review I'd like to point to here, I think is excellent, also talking about function and architecture within and between muscles. That also came out, I've seen 2011 was the time. But the whole idea here, or the whole theory here, is that our normal or traditional way of thinking is that we have a muscle loading up a part of the structure and then loading the tendon here. But what if there was lateral force transmission that spread through either through the muscles or through the tendon laterally? This would mean a greater cross-sectional area. It would mean a reduction in stress in the tendon here, and this could perhaps mean have influence on injury in these loaded tissues. Another way of looking at it is more longitudinal, that you could say, is there a path of greatest resistance? This is something that's talked about in muscle, but could this also be in tendons? Think if these tendon units here are closer linked than the others, if the muscles are activated, then much of the strain would be going through those where the greatest resistance is. And this would in theory mean that you have a smaller tendon inside the greater tendon, and this smaller tendon would then have a greater stress. So in animal models, this has been published quite widely, and the term myofascial force transmission has been used. And these authors here, they are able to show that if you activate your gastrocnemius, it's possible to measure force in not only the adjacent gastrocnemius or the soleus, but also in the antagonist on the other side of the joint. And this is an evidence, at least in a rat model, outside ex vivo, that force can be transmitted between muscles. So in our lab, we tried. We would like to do this in a human in vivo model, and we tried this with ultrasound. And the idea was basically to look at the interface between three muscles here. So the idea was to do passive knee joint extension and to see could we see movement in some of the other muscles with ultrasound. Another idea was to do passive toe extension, which would elongate the flexor hallucis longus, and could we then see movement here? Another idea was to do stimulation of the gastrocnemius here, again to see if we could see movements going on. And with this model here with ultrasound and different joint configurations, we were able to show that it seems that there can be lateral force transmission in humans also between the superficial plantar flexor muscles. That means inside the triceps surae. But we could not from these data show that there was a lateral force transmission from the triceps surae and into the more deeper plantar flexors. Yeah. So we'll just skip this and come to the conclusion here, because the latter data here were basically similar data done with MR. So to the two questions that I put up in the beginning was if tendons transmit force in a homogeneous or linear manner. I think there's significant evidence to state that this is not necessarily always the case, and I think it may have functional relevance in situations where movements have to be fine-tuned